In this short video, I want to capture the essence of the first part of section 9.3, which discusses and gives examples of the connection between linear velocity and angular velocity. The fact is that under certain circumstances, there is an easy and natural connection between these two variables. Let's first consider a free spinning shape. So here I'm imagining a disk or a cylinder or a sphere that's spinning about an axis of rotation. In this diagram, the axis of rotation is marked by the cross, and the angular velocity at which it's spinning is indicated by omega. And here with that swirling arrow, I have it spinning clockwise. The question is, if you pick a point a distance r from the axis of rotation and ask how fast is that point moving in meters per second, there's often an easy way to figure that out. But there's one thing to keep in mind before we go too much further. All the objects that we're going to consider in this class are called rigid rotators. And rigid rotators have the special property that every point on the body has the same angular rotation rate, omega. Whether it's near to the axis of rotation or far from the axis of rotation, omega is everywhere the same. If an object spins in such a way that omega isn't everywhere the same, then it would have to twist up on itself. And that's not what we would call a rigid rotator. So for a rigid rotator, all points on the body have the same angular rotation rate omega. But it's pretty clear that different points would have different speeds. I mean, if you think about it, a point that's close to the axis of rotation doesn't have to go very fast to go around once in the same amount of time that a point that's far from the axis of rotation near the edge would have to go around. So the linear speed of a point on a spinning body depends on how far it is from the axis of rotation. And the formula is pretty simple. The speed of a point on a free spinning object is called the tangential velocity. And it's equal to the product of omega, the angular rotation rate, it's got to be in radians per second, and r, which is how far the point is from the axis of rotation. So it's called the tangential velocity because it has to be perpendicular to the line that goes from the axis of rotation to the point. If it weren't for that, the object would be like stretching out in the radial direction or getting smaller. So in summary, it's pretty easy to find the tangential velocity of any point on a shape that's free spinning and also a rigid rotator. It's just equal to omega times r. Now there's another circumstance where this same formula is used with a slightly different meaning. So here I'm imagining an object that's rolling without slipping. So like a wheel, for example, rolling across a level surface. The axis of rotation in my diagram here is still marked by the cross at the center. And the object has a fixed radius now equal to capital R. Now you might ask the question, if something rolls without slipping at some angular speed omega, how fast is the center of the object actually moving? Well, the answer is pretty simple because it's the same formula that we had before. I guess it's useful to point out that for something that rolls without slipping, the actual part of the wheel, for example, that's touching the ground isn't moving at all because the ground isn't moving. But the center of the object has to actually be moving forward. It's almost like instantaneously the wheel is rotating about the point of contact between the wheel and the ground and not about the axis of rotation. But thinking like that could be a little bit misleading because this is a combination of something that's spinning and moving at the same time. In any case, the velocity at the center of a rotating object, if it rolls without slipping, is the same formula we had before, omega times r. But here r takes on a slightly different meaning. It's the radius of the object that's rolling. But there's one other thing to consider, and that is, what about other points on this body? Like, for example, the very top of the wheel. How fast do you think the top of the wheel is moving? So the bottom of the wheel, where it touches the ground, isn't moving at all, because then the wheel wouldn't be rolling without slipping. The axis of the wheel, the axle that it rotates around, has to be moving at a speed, the speed of the center of mass, which is equal to omega times r. What about the very top of the wheel? Well, if you thought this through right, I think you would get correct that the top of the wheel has to be moving twice as fast as the center in order for the thing to continue to roll as a rigid rotator.